Today's presenter is Aaron Smith, Application Technology Manager of Tensar's Grade Separation Solutions Group. He's worked in the mechanically stabilized earth retaining wall industry for more than 13 years and has been involved in the design, sale, and marketing of multiple systems and products.
Thank you, Bob. I'd also like to thank you all for joining us for today's demonstration of TensarSoil Software. We have some learning objectives outlined, and these objectives are to use the TensarSoil software to efficiently design MSE retaining walls, to apply various live and dead load surcharges to the design analysis, compare multiple Geogrid layouts for project cost efficiency, design with NCMA and AASHTO LRFD methods, and to generate alternative wall designs for several wall facings. After this webcast, you will be able to obtain the TensarSoil software. We will send a license agreement and software link to all attendees, and please send the completed license agreement back with the registration code request. And for those viewing the recording at a later date, contact Tensar at web@tensarcorp.com for the license agreement and software links. The license agreement and software link will be sent to all attendees of today's webcast within about 1 week from today. Now we will move on to the software demonstration. This screen is the initial screen when you launch the software. We will begin by clicking on the File drop-down menu. From here, you can select English units for your design, you can adjust your toolbars, and you can also enter user details. By clicking on the user details, you will see the user details window shown here. It is important to enter the user details correctly, as all of this information will automatically fill into your printout screens and for your cross sections. The language options are not fully available at this time. Those are available in future updates. Back to the main screen for the software, you will begin by selecting your project region, which should default to North America. Next, you will check a box for reinforced MSE wall design and uncheck a box for reinforced slope, which is number 2. A wall is defined as a 70-degree or greater structure from horizontal, and a slope is defined as flatter than 70 degrees from horizontal. Box 3, you will check when applying seismic loading. This can also be selected later on in the software. Box 4 is to choose whether the design you are working on is for a public or private project. Your 5th selection will be to choose your design method, which is appropriate for your project. NCMA is the most common private market design method in North America. Step 6 is to uncheck the English units box to move forward with metric units, or leave it checked for English units. And step 7 would be to click on Make a New File to start your design. This is the main design screen that you will see in the software, and we'll be coming back to frequently. On the top left is the geometry input area of the screen. In the middle of the screen is your design cross-section, and on the top right is the Geogrid entry and modification window. And at the bottom center of the screen, you have the horizontal stresses window. We will begin by reviewing the icons at the top of the screen. These first 4 icons will be fairly obvious as to what they do. The first icon, circled in red, is to make a new file, and the second one is to open a file, to select an existing file from your directory. The next icons to the right are Save the File and Save the File As, which also are very similar to other icons in other programs. The next icons to the right are your print features. The first is the summary print, which you would select to print the summary of the design case with detailed calculations excluded, followed by the detailed print, which would be selected for a detailed print of your design case, including all the detailed calculations. These would be selected after you have completed the design section, so we will review the print features later in the demonstration. The next icon is the facing system selection. In the next video, you will be taken through the selection of your facing system.
System icons located here and here will bring up your facing system selection for your design. The systems available for the design are mesa retaining wall, temporary walls, Sierrascape systems, or the Sierra Slope retention system. For this demonstration, we will select the mesa retaining wall system, and you can do so by either checking the box that says select or on the image to the right for that system. With the mesa system, we have the ability to design with the DOT connector. For public designs or for private, we would use the standard connector. And then we can choose whether the system will be designed as near vertical or with a standard batter. Over on the right, you can see the different input areas. The first one is the facing angle. So when we selected the near vertical option for batter, we are selecting an 89.55 degree from horizontal retaining wall. If we selected the standard batter, it would change it to an 85.5 degrees face angle. We'll use the standard selection for now. You can adjust your wall height. Let's change it to, say, 25 feet. Below that is an area for the spacings of the geogrids, and it defaults to a spacing of 8 inches, and that's because the blocks are set at 8 inches. So you cannot have geogrids at mid-height of the block. They need to be at the tops or bottoms of the blocks. So it is defaulted to 8 inches, and that is unchangeable. You can change the minimum and maximum spacings for the geogrid from 1 times this 8-inch height, and then the maximum could be up to 3 times this 8-inch unit height. Again, the grayed out area would be non-changeable. The areas that are black can be changed in text. Extra grid length to form the connection is defaulted to 4 inches, and that's because the geogrid overlaps the block 4 inches. Percent plan coverage of geogrids is set at 100%. So in plan view, your geogrid will be continuous from left to right across that elevation for the section you're designing. The max number of blocks below the first grid allows you to change it from 1 or 2, so that way you can adjust the elevation of the lowest grid layer within your design section. Down below are the block sizes as well as the weight of the block. We'll leave this as it is, the default values. And then you have the center of gravity distance, your block interface parameters as well. If you want more details of the system you're designing, you can click on Show Details of Facing, and it will load your design system, an architectural rendering showing the components of the system of what you're designing. You can see here we have the Mesa standard connector anchoring the geogrid into the block, and there's some flags on the connector, and because of the way they're oriented, they will push against the core of the block above, which will give you the batter on the wall shown here in the image. When you're done, you can close this out, and we are ready to move on. So let's click Set, and it will take us back to the design input screen.
Continuing with the icons at the top of the screen, the next icon to the right is the geogrid lengths icon. By clicking on the icon circled in red, you will see a grid lengths window pop up. This is an area where you can increase the geogrid length of the top geogrid layers to satisfy pullout if needed. In some cases, you may find the overburden depth is insufficient to provide pullout resistance of the uppermost layers of geogrid. By lengthening those layers, you increase their pull-out resistance. You would come back to this window after you have completed the design and only if the upper layers are failing in pull-out. You would click OK to exit this window. The next icon to the right is the secondary geogrids. You would use this to add secondary biaxial geogrids for the reinforced slope system with a face angle less than 45 degrees from horizontal. We'll move past this one for now. The next icon, circled in red, is the surcharge loading. By clicking on this icon, you will see the surcharge loading window appear. In this area, you can enter up to 5 different surcharge loadings. You can click on the live or dead buttons to switch back and forth between those 2 different loading conditions. And at the bottom, circled in red, you will see it says distances are measured from toe of reinforced fill block. By clicking on that button, you can change it to distances are measured from the top of the reinforced fill block or from the toe by toggling back and forth. When you're done, click Set to continue. The next icon to the right is the horizontal load. You'd use this to enter horizontal loading acting on a wall. Here are a few examples of horizontal loading that affected a wall's performance. Horizontal loading can control the upper geogrid requirements and is important to consider in your design. So by clicking on that icon, you'll see the window pop up where you can enter up to 5 different horizontal loads which are input with X and Y coordinates from the lowest point of the wall at the face, being 0, 0. When you are done, you would click Set. The next icon is for earthquake loading, or seismic accelerations. By clicking on this icon, you will see one of 2 windows, depending on the design method you're using. This first one would be an example of the NCMA seismic accelerations. Here you would input the appropriate earthquake design parameters for NCMA in the horizontal acceleration. The proportion of live load to use during earthquake is 0 per NCMA, but the engineer may use his or her judgment to change the temporary surcharge load to some percentage of what the surcharge loads being applied to the top of the wall are, with 1 being 100% and 0 being 0%. This next slide shows the LRFD seismic accelerations window. The main difference is that the proportion of the live load to use during earthquake is set at 0.5, which is defaulted per LRFD. The next icon to the right is the water pressures, where you'd enter your water pressure locations. Clicking on this icon circled in red will bring up the water pressures window, which you see here. So if it is appropriate for your design, you would select this to add water, either standing water in front of the wall or within the reinforced fill if needed. When you're done entering the data, you would click Set. And the next icon to the right is simply a toggle as to whether water is at the foundation of the wall. By clicking the icon, it will apply water at the toe of the wall, below the wall, and by clicking it again, it will remove the water from the foundation of the wall. The next icon would be the fill and foundation soil properties. So by clicking on this icon, again circled in red, you will see the soil properties window pop up. In this window, you can enter in the first column would be cohesion, the second would be the phi angle of the soil, And the third and fourth columns would be the bulk density of the soil that you are inputting. It is important to note to use the peak angle of friction for retaining walls. The maximum particle size in the reinforced fill will affect the reduction factor of the Geogrid for installation damage. So it's important to get the appropriate particle size selected here. When you're done, you can click on Set. The next icon to the right is the Geogrid class and strengths. And this is where you can input the Geogrid design parameters and the design life of the retaining wall. By clicking on the icon, you will see the Geogrid strength and design life window pop up. Here you can enter the appropriate structure design life in the top left of the window. And you can also adjust the maximum particle size for the fill and foundation properties input. If you change it in this window, it will revise it in the soil properties window as well. So they both will work. You can adjust in either location. You will also want to select the appropriate Geogrid class from the drop-down cursor. It shows here on this window as UX Public Clients, but you can also select Private. And that has to do with the reduction factors for the Geogrids. To review those reduction factors, click on Review Design Parameters. Clicking on Review Design Parameters expands this window as shown here. You can now see all of the reduction factors and factors of safety that go into calculating the T allowable for each Geogrid. You can also adjust the installation damage and durability reduction factors as needed, with maximum reduction factors being 1.5. The default will always be available if you click on Set Default Installation Factors, though. When you're done changing, you would click Set and then click OK. This brings you back to the main window, where the next icon to look at would be the Geogrid interaction factors. By clicking on the icon, you would see the grid interaction factors window, where you can input the coefficient of sliding on the Geogrid, and also for pullout of Geogrid, you can check the box that says replace CI values for all Geogrids with values given below. And you can make those adjustments here as well. When you're done, click OK. And the next icon is the cost data entry, a small dollar symbol. This is where you can input the cost of the Geogrid per square meter or square yard of face to estimate the cost per meter or foot of your wall design. By clicking on that symbol, you would see the cost data entry form. So you would select which Geogrid class or type you are using for your design, input those costs of Geogrid per square meter or square yard, and for pricing, it'd be appropriate to contact your Tensar local regional manager for estimating purposes for your design sections. And I'll show you how this comes into play later in some videos. The next two icons, shown here circled in red, are for the external stability calculations. The first is the calculation of external stability, which is a quick review of external stability calculations, and the next, to the right, are detailed forces and moments for external stability, which you would click to quickly review the forces and moments in external stability calculations rather than printing out the summary and having to review that in detail. The next icon to the right is the internal stability calculations, which you would also click to quickly review the internal stability calculations rather than print out your full design section and review it there. Now that we've reviewed the icons along the top of the screen, we can begin designing a retaining wall. This next video will show you how to enter the project geometry and complete a design section.
On the left of the screen is the geometry input form. And as we make changes to the geometry, you'll notice that the area beside it, shown here, is our live cross-section. So every change we make in the geometry will change as we do it live. So let's add a top slope to the cross section. It defaults in at a 3-foot top slope with a 24-degree angle from horizontal. If we wanted to change it, we would simply click and highlight over the text, change the text, and click set. But I'm going to go ahead and leave it as a 3-foot top slope for now. And 24-degree angle looks good. But you'll notice that after applying the top slope to the cross section, the live load and dead load surcharges maintained their horizontal offset from the top of the wall. Let's click back on the surcharge loading icon, pull up that window, and now we have a third option as far as where the surcharges are measured from. So let's click on distances are measured from the toe of the reinforced fill block. We will now change it to the top of the reinforced fill block, and let's click one more time, and now it's measured from the crest of the top slope. So now we can zero out the left ends for both loads, put back in the right ends as being 300 feet offset, click set, and now you will see our surcharges have both been moved to the crest of the top slope. Now that our geometry has been set, we can work with the geogrids in the Modify Grid Layout screen, and also looking at the horizontal stresses shown in this window here. Our aim is to get our geogrid contributing strengths beyond this red stress curve. So this graph is from 0 feet in height up to the top of our wall, and then it's the stress at that elevation from starting at 0. So you can see at the bottom of the wall the stresses are greater, and at the top of the wall they are less. What we need to do is make sure that all of the endpoints of the geogrids end beyond the red line here. Now this is not the geogrid lengths, this is the geogrid contributing strengths. So every point that falls to the left of the red line is failing and is not sufficient for the design, and in this case it notes that it's failing in CON, which if you look at our key here is connection. So these geogrids here are failing in connection, the next 3 are satisfactory, and then we have a couple of grids that are failing connection and are non-existent. They're not, we haven't filled in all the geogrids to the top of the wall yet, as you can see in our cross section. So the first thing to do would be to add geogrids up to the top of the wall. The default on the program is to bring in 9 layers of geogrid plus 1 base grid. And you can see in the Modify Grid Layout window here, our groupings are based in these columns. We have the number of layers of the geogrid, the type of the geogrid, the spacing of the geogrid, and then up to what level they occur from 0 at the toe of wall, the percent coverage of all of the geogrid layers, and also the C sub I value, which can be adjusted per grouping. Let's go ahead and add some more layers of UX 1400 up to the top of the wall. And you can change the type of geogrid simply by clicking on the geogrid label. So we can cycle back through UX 1400 and we'll add some more layers at 24-inch spacing to get us to the top of the wall. So now you can see we have the base geogrid layer, this one, failing in connection. Then the next 1, 2, 3, 4, 5 failing in connection, and that's 5 out of these 9 are failing in connection. And then the very upper layers are failing in pullout. Let's first adjust the grids at the bottom, and we'll work our way from the bottom of the wall to the top. So we know we need to improve this layer of geogrid, the base geogrid. So let's click on the 1400 MSE label, and now it will be UX 1500. You can see it is now changed to a pink layer of geogrid, so you can differentiate it visually between the different types of geogrids. This one is now satisfactory. Now we need to change these 5, but they're part of the grouping of 9 layers of UX 1400. So in order to do that, let's drop this down to 5 layers and click on the 1400 to change it to UX 1500. And now we will add more layers of UX 1400 up above. Okay, now we have all of the layers at the bottom of the wall are satisfactory, but the upper two are still failing in pull-out. Now earlier we talked about this icon here where we can adjust the grid lengths. So I'll click on that, and we can add Geogrid length just to a couple of those layers. So we have 2 layers failing in pull-out, so let's adjust the top 2 layers, and let's add 2 feet to each. Click OK, and in our cross-section you can see the upper 2 layers of Geogrid are 2 feet longer than all of the Geogrids down below. So we can adjust just the upper layers of Geogrid without affecting all of the Geogrid for the design. Now our design looks like it's satisfactory. Let's check external stability here on the left-hand side of the screen. You can see sliding factor of safety is 2.675, bearing is 5.388, and overturning is 3.092, and all of these are okay. And now we can check internal stability, and both internal sliding and internal stability are satisfactory. So if you look up here at the cost per linear foot, this design is $57.99 per linear foot of wall. That's just for the Geogrid based on the grid cost we entered with this icon earlier. But we could try to do a little bit better. Maybe some of these layers of Geogrid here are a little bit over-designed. So we already tried UX 1400 at 24-inch spacing, but we could reduce the spacing to 16 inches by clicking on this down arrow, and then we could reduce the number of layers of UX 1500 until all these layers drop down closer to that red line. And now let's add some 1400 at 24-inch spacing up above, and we can drop maybe a couple of these out. Now I dropped too many. You can see the connection failed. We'll add one more back in, and add one in at the top, and now we're at $62.79. So that actually increased the cost of the wall. Perhaps we could go to a weaker Geogrid altogether and go to UX 1100. And maybe we could go to 1100 here as well. Well, we have one failing connection. If we add one layer of 1500, now that takes us to $53.76 per linear foot. Still looks like we have one layer perhaps over-designed, so I'll drop one layer out, and there we go. Now we're at $50.56 per linear foot. So we'll check the external stability, check internal, and that looks like to be the most optimized design we could probably get out of this. $50.56 per linear foot. Alternatively, you may look at this and say, I'd like to do this all with one type of Geogrid. What if we just changed it all to UX 1100? Could we optimize it with different spacing? So let's go ahead and do that. If we drop this down to 8 inches, now the wall passes $58.57. So all with our weakest type of Geogrid at different spacing, we are at $58.57 per linear foot. Or you can maybe go with all 1500 and try 24-inch spacing for the whole wall height. So we'll increase the layers, and we're at $63.82.
Now that we have designed a Mesa segmental block wall, we can now change the facing to an alternate system. The next video shows you how to do so.
We've designed a Mesa retaining wall system with the input that we've used. We can also look at changing it to a different system and see if that would have any effect on the Geogrid layout and cost. We can easily do this by clicking on one of the facing system icons, and let's change it to the SierraScape stone-filled system. By clicking select, we can leave the batter of the wall at the same as it was for Mesa, or we can design with up to 90 degrees with the SierraScape system. You'll see that the spacings of the geogrid are now set to be a multiple of 18 inches, and that's because the basket height is 18 inches. So we will have some difference in the geogrid layout. Also, 94% plan coverage of the geogrids is used because SierraScape system typically uses two widths of UX HDPE geogrid side by side over the basket width. So we have 94%, which is our standard. And when we're ready to progress, select Set and click Yes, and it will automatically utilize the geogrid layout that we last used for the MESA system as best as the program can make it fit. So instead of 24-inch spacing, we are at 18-inch spacing. And now let's add some layers of geogrid to get to the top of the wall. And you can see that the geometry has all been maintained, the loading conditions have been maintained, and the geogrid is now over-designed. Again, we went from 24-inch spacing down to 18-inch spacing of UX 1500. So we can optimize this slightly by adjusting the layers, adding some 1100 at the top. And you can see we are now at $60.51 per linear foot for this design section. And perhaps there could be other modification and optimization done for the geogrid layout. But that shows you how quick it is to check two different systems with TensarSoil software.
In the next video, we will change this design section back to the MESA system for an LRFD design.
Now we will change this wall over to MESA and do a LRFD design method. So let's select one of the two facing system icons, select the MESA system, DOT connector, near vertical. We'll leave the design height the same. Again, the spacings are set at 8 inches, which are the block heights, with a minimum grid spacing of 1 times 8 inches and a maximum of 3 times the 8-inch block spacing. 100% plan coverage of geogrids, and now we can click on Show Details of Facing. You can see in this rendering that we have a near vertical alignment on the left, as well as the MESA DOT connector as the geogrid connecting device to the block face. We'll close this out when we're done and click on Set to move on. Next, a window will pop up asking us if the grid coverage will be set to the default for the rest of the facing. Click on Yes. The grid interaction factors window will pop up, and the software is making sure that we don't want to change any of these factors when we change to a different design method. Click OK. And again, with the fill and foundation properties, the same. Click Set. On the left-hand side of the screen, we'll change the design method to AASHTO LRFD. And again, click through the interaction factors and the fill and foundation properties as OK. So now we will change the geogrid to optimize it for the design. The software tried to maintain the spacing as best it could, but it dropped it down to 8 inches from the 18 inches for the SierraScape system. So we'll make sure our base grid is set at the top of the first block at 8 inches. And now let's try the 24-inch spacing we use for the NCMA design method for the MESA system. And you can see that we have some geogrids failing in connection strength at the bottom of the wall. So we can either change the spacing of the geogrids down to 16 inches, and that passes at the bottom, or we could change it back to 24 inches and change the geogrid strength to UX 1600. And now we have a suitable design. It's not perfectly optimized. As you can see, these endpoints of the geogrids are well beyond the red stress curve. So we could drop some of the geogrids down, perhaps change these to UX 1500, and then add some layers of 14 or 1100 at the top. At 24-inch spacing, and fill into the top of the wall. Bump up the layers below the 1100, And there we go. So now we'll check external stability, and we get a note saying the sliding CDR is not valid as the resultant is not in the middle third of the wall, and that is because our embedment length is not adequate for the design height that we're running. So we will change this to 7/10 the wall height, which would be 17.5 feet. Click Set. Check external stability again, and check internal stability, and we'll see we do have one failing connection here. We'll add another layer of 1600 underneath, drop out some of the 1500. Check external, check internal stability, and we're okay.
Another feature of the software is the ability to adjust the percent coverage of certain groups of geogrids. The next video demonstrates how to do this.
Is at 100% coverage in plan view. So one roll of geogrid abuts directly up against another roll of geogrid, side by side. What you can do is separate out some of the layers of geogrids into separate groups and reduce the percent coverage for the wall. That can be helpful if we had some guide rail posts or signposts at a set interval. So let's take off the top slope in this case. We'll go back to the live loading and the dead load, the surcharge loads. We'll now move those over towards the face of the wall, top of the reinforced fill block. Let's say they are maybe 3 feet back from the wall face. Click Set. And now let's separate out the top 2 layers of geogrid so we can reduce the percent coverage on just those 2 layers. So we'll take out 2 layers of geogrid and then add a separate group up above at 24-inch spacing. And now we can reduce the percent coverage down to whatever the repetitive obstructions equal out to. So let's say it's an 85% coverage. So maybe some guide rail posts at a repeating interval. We'll click Set. And now we've applied the reduction in percent coverage just for the upper 2 layers, and you can see they're still passing. Now this upper layer of geogrid may be too close to the wall, to the top of the wall, so let's change that one down to 24-inch spacing. We'll add 1 layer at 16-inch spacing and reduce the percent coverage there as well. Click Set, and we'll change it to the 1100 geogrid as well. Now let's check for external, check internal, and now we've applied a reduction in percent coverage on a couple layers of geogrid at the top of the wall.
It is important to remember to enter the horizontal loading when necessary. To recap, that is shown in the icon circled in red here. We have demonstrated a few retaining wall designs. Now we will demonstrate laying out a reinforced slope using the design software in this next video.
By clicking on the New Project icon located here, we are brought back to the main screen. Now we will design a reinforced slope with the software. In the previous discussion on walls, we talked about the software's ability to design around standard industry methods such as AASHTO LRFD and NCMA, which are the most often used. The agency, particularly in the public sector, will often dictate by statute what methodology is to be used. In the private market, it is often up to the engineer to decide, though, based on the application. When designing a slope, there may be prescribed methods for analysis dictated by statute. However, often there aren't prescribed industry methodologies. Instead, there are standard industry practices that might be used simply based on the preference of the engineer and based on what the engineer is designing. For example, the design may be preliminary slope design, or a full global slope analysis. For preliminary slope design, the software uses a two-part wedge mechanism. So down here, we will uncheck the box where it says face of structure 70 degrees or steeper. By unchecking this box, you will see the design method available in the middle of the screen is the H86894 method. The two-part wedge is a standard stability analysis technique that addresses base sliding as well as internal and superficial stability. And in the software, we use the British HA94 method, which is an elegant method common in the UK. We can provide a detailed description of the HA94 method upon request. Now that we've selected the design method, we will decide if this is a public or private project depending on who the owner is and what the requirements are. And then we'll decide if we are going to use English units or metric units by checking or unchecking this box. For this analysis, we will use English units. And now we will click on Make a New File. You'll see a window pop up with the file name, which we have not saved yet, so it says No Name 1 in the top of the window. But the window itself states that the HA6894 method is only for static internal stability analysis of slopes with face angles less than 70 degrees. And the factor of safety is actually provided by using the constant volume phi angle of the soil, not the peak. Overall stability, compound stability, and seismic loading should be verified with stability analysis using a suitable slope stability program. Tensar has a global stability program called Tensar Slope, which is available through a separate design seminar. And if you're interested in that software for global stability analysis of slopes as well as retaining walls, please let us know. Once we acknowledge this, we click OK, and we are ready to begin our design. The first step when designing a reinforced slope is to select which type of facing we're going to use for the slope. It's the same as the first step for retaining wall. So we can click on either of these two facing system icons and bring up the facing systems window. Let's scroll down to the reinforced slope system, Sierra Slope, and we need to decide what facing angle our slope is going to be designed to. Tensar recommends that for any slopes steeper from horizontal than 40 degrees, which is roughly a 1.2 horizontal to 1 vertical slope inclination, we would recommend using a welded wire face basket as a construction tool at the face of the slope. Once you're flatter than 40 degrees, you could either go with a slope wrap face or a Sierra Slope graded face. I'll show you what these images look like here. It's a wrap face, there's no baskets, and then this would be just a graded face. Let's design a 60 degree slope, so we will select the welded wire fabric vertical basket. It is now selected. We will set the facing angle to 60 degrees, and let's design a 35-foot tall slope. Now the basket heights are set at 18 inches as a default. That is the industry standard available basket. So we will leave the default spacings at 18 inches, but we can have a minimum of 1 times 18 inches. That means the Geogrid will fall at the bottom of every basket, but we can allow the Geogrid to span up to 2 baskets, so we can have up to 36-inch spacing between Geogrid layers. We will use 100% plan coverage of Geogrids, so we will not use percent coverage, although we could. And then the level of the lowest grid above the datum, above the toe of the structure. Let's leave that at 0 inches so all of our Geogrid layers line up with the bottom legs of the baskets. Now I'm going to click on Show Details of Facing to show what we are designing specifically. So you can see we have the welded wire form. We're going to have a BX Geogrid wrap, which is shown here in a gray color, but it's actually carbon, it has carbon black included, so it is a black product, but for illustration purposes it is shown as a whitish gray here. And that wraps the face of the basket. Inside of that we have an erosion control mat, and then the topsoil. And then the uniaxial Geogrid would come in at the bottom of every basket or every other basket, depending on what our design tells us. done looking at this facing detail, we can close it. And now we can click the Set button. So you can see in the geometry form here, we have a 35-foot tall slope, 60-degree facing angle, and in our reinforced slope cross-section, you can see that's been replicated as well. Now let's enter a live load at the top of the slope. And let's say it begins 3 feet back from the top of the reinforced fill block. And maybe it's a 250 PSF live load. We'll click Set. And that load is being applied at the surface. We could enter water pressure data if we wish to. I will leave that off for this demonstration. The next item to check is the soil properties. This box is a little bit different than the retaining wall designs. You can see we have just one type of fill to enter, and that's because the software for reinforced slope design would be, you'd be entering the weakest soil properties that you have. So it's assuming that your foundation, your reinforced fill, and retained fill all have the same properties. And another important note is that we're now using the constant volume angle of friction. So most tests will give you the peak angle of friction. If you do not have the constant volume angle of friction, you can check this box which says assessing the fill shear strength in cases where constant volume values are not available, and you can now enter in your cohesion, your phi angle of the peak angle. So say we had a 34-degree phi angle as peak, and the factor of safety you wish to apply, and then it will back apply this factor of safety to the peak angle to use the constant volume. So let's say we do use a 1.3 factor of safety and click Set, and now this 34-degree peak friction angle is 27.42 constant volume. We will choose what particle size to apply, and this again, same as the retaining wall, will influence the installation damage of the geogrids. We'll leave it at 3/4 inches and click Set. Next we will look at our grid class and strength properties. And the program defaults to 60 years for a reinforced slope. We can bump that up. Let's say we're doing a 75-year life. Let's review our design parameters. Sorry, this window pulled up off screen. So 75-year design, click Set. And we have installation damages of 1.1, durability reduction factor of 1.1 because we used a public client. And once we're done reviewing this, we can click Set and OK. We can look at our interaction factors again, which for sliding and interaction for pullout, our default values are 0.8 for both. You can change those if you wish, and if you do make a change and want to go back to the default values, you can always click on default values in the bottom left here. Let's click OK, and let's make sure that our cost data was entered correctly. So these were the default for the program when I pulled it up, 1, 2, 3, 4, 5, 6. Let's put in 2, 250, 3, 350, 4, and 450. And this is just for estimating purposes to compare the efficiency of our design. If you'd like actual cost data, I would recommend you contact your local regional manager from Tensar and get those values to use for your program if you want it to be specific to your region, or you can contact your distributor for that as well. And when you're done, click OK, and we are ready to click Proceed at the bottom of the screen here. Now this window is going to be different than it was for the retaining walls. I'll explain that in a moment as we go through the process. But we will want to keep the geogrid lengths equal for this preliminary design of reinforced slopes. So click on Go Proceed, and now the program is telling us it will first determine the T0B mechanism, which gives the minimum length of reinforcement at the base. So it's determining how much geogrid embedment we need at the base to prevent sliding. Click on Go Proceed. It's saying the required T0B mechanism length is 25.28 feet. Now it's going to determine the Tmax mechanism to find minimum reinforcement required. Click Proceed again. it requires a minimum number of layers of the weakest grid to be 12. And the theoretical depth of the top layer is just 5.05 feet. But again, we checked on the box to keep all geogrid lengths equal. We'll click proceed again, and now it gives us an opportunity to change that base length to an even increment. Let's change it to 25.5 feet, click set length, and go proceed again. Now we see this HA6894 window down here at the bottom is slightly different than what we've seen on the retaining walls. This is no longer a stress curve that we're trying to make our geogrids come to the right of. Now this is a spacing curve of the geogrids that are in the design. So the modified grid layout screen here is very similar, it is exactly the same as the retaining walls. But let me change some of these geogrids. You can see it's saying the spacing is not okay at 36 inches of this geogrid. I'm going to change one of these geogrid layers in this group as well to UX 1500. And I'll change a few layers so maybe I can explain this better for you. The 1500 curve is here, and it's saying that the 1500 can be spaced at elevation 0 at 36 inches, and it will be suitable, just barely. It almost comes exactly to that point. But with UX 1400, we would have to be somewhere around perhaps 22, 23 inches in order to be a passing design and have the spacing okay. So this is all about the spacing of the geogrids, not about the strengths at this point in this software. So we need to make sure that the spacing is okay, that all these points fall to the left of the curve line for that strength geogrid. And we can do that by adding geogrid up to the top. We could have also changed the spacing of the geogrid. Instead of keeping them all at 36 inches, we could drop them down to 18-inch spacing, and you will see that now at 18-inch spacing, these points are still to the left of that spacing curve, so we're okay. And now we can jump up to 36-inch spacing at roughly elevation 12. So we can now add layers of geogrid up above. We could also potentially make this geogrid weaker, so let's click through the names of the products, and now UX 1100 is green, and you can see that the spacing is not okay because at this elevation here, our UX 1100 should be no more than roughly 30-inch spacing, but we have it at 36. So we'll add a layer of geogrid below, add another one in the third, and let's add a layer at 18-inch spacing at the top, just so we have some more geogrid towards the top of the wall. There we go. And now we can click on Go Proceed. And now we're going to check through Tmax and do a thorough wedge check. What the software is going to do is check a two-part wedge at every elevation of geogrid. So it's checking all the base widths at every layer of geogrid as if we're creating a two-part wedge at the elevation of the geogrid, and then coming back at a steeper angle at every elevation. And I'd be happy to supply a thorough description of what the software is doing and what the HA6894 two-part wedge method is checking here. But you can see we just ran hundreds of iterations or thousands of iterations of two-part wedge checks at varying angles from the back slope all the way up to the surface of the structure. But once we've done this, it says that we are okay with the internal stability. You'll notice the external stability note says foundation is assumed to be competent. Again, it is critical you design this with a global stability software and check it as well, such as our TensarSoil software or any other. But this gives us an efficient way of designing the geogrid in an optimal way, so that way you can efficiently and quickly come up with a layout for your geogrid which you can use to put into your global stability software for a final check. Once you're done, you can click on either of the print features and move forward with your printing of your calculation.
Once you have completed your design case, you can click on either of the two print icons shown here circled in red. The detailed print is more thorough than the summary print, as we described earlier. Clicking on either of the icons will bring you to this print control window. On the left, you have data entry fields, and on the right, you have a print preview area. To zoom in and out, you can click on the two icons circled in red here, which will take you closer and further away from the print preview image. And clicking cancel will bring you back to the design case. Any information already entered will be saved, so it is okay to click cancel at any time to go back to the design case. To preview content in other pages, you would click up or down on the cursor where it says page. And to the left is the input project information, which will be printed in your output. On the left, you have output options, circled here in red. You will notice that there's a final design box. By checking on the final design, the disclaimers in the first page of the printout will change from preliminary to final, and the notes will change accordingly. You also have the ability to add extra pages to your numbering of the printouts. So by clicking where it says extra pages, you can add one or two or however many extra pages you want, and it increases the numbering only. It does not provide actual blank pages within the printout, and this can be handy if you have some hand calculations that you want to include. There's the ability to scale the text for the printout if it is too small or too large for your printout. And you also have the ability to select whether you want to draw the geogrids, which are shown on page 2 in the cross-section. Still on page 2, you will see there's a drawing menu toolbar where you can now add lines or add text to your image where it prints. You can click on Add Text to begin adding text anywhere in the printout. And when you're done, click Stop Adding Text. You can also add lines with arrows if you want to label things more specifically. So you would click on Add Lines, and you're done, click Stop Adding Lines. To delete a line, you would select the line and then click where it says Delete Line. Another feature is the ability to hide the geogrid names, which the geogrids are shown on page 4. So you would check this box to replace the geogrid names with generic terms such as type 1, type 2, type 3, etc. To print the summary of the content, you would just click on the print file, the print icon. And when you are done, you would just hit cancel, and it will take you back to the design screen. We have one more brief video showing how to initially install the software.
TensarSoil Software. You can open the zip file and extract them, save the program to the location of your choice. And when you open the folder, you will see several subfolders, including design examples, presentations, program files, program manuals, and also the license agreement. The design examples folder includes a Mesa retaining wall design example, as well as the HA method for designing a reinforced slope. In the presentations folder, we have an introduction to Tensar systems and the design methods in the software, as well as the software setup. In program manuals, we have more information on the Ashstone NCMA design methods, information on the HA6894 reinforced slope method, as well as the program setup overview. And then finally, in the program files, we have the TensarSoil Software with several subfolders that you'll leave as they are, but you will then see the application file TensarSoil, and you can create a shortcut on your desktop by clicking and dragging and creating a shortcut at your preferred location, so the program is now easily accessible from your desktop. When you launch the program for the first time, you will see a user authorization window pop up. And inside this window will be a sequence of numbers, which you can see here. And that sequence of numbers will change from computer to computer. So if you have the need to install the software on more than one computer, you will still need to have multiple authorization codes. So you can copy this string of numbers and put them in an email and send that email to web@tensarcorp.com, and then we will respond with the registration code for your computer. Once you have the registration code, you can enter it in this box here and click OK. Now a window has popped up on my other screen here asking if your location is currently set to the United States. Is this correct? Click yes, and now you are able to run the software.
For those interested in hearing more about TensarSoil additional training or about our Tensar Slope Global Stability Program, please contact Tensar. Again, a license agreement and software link will be sent to all attendees of today's webcast within 1 week. Please send the completed license agreement back with a registration code request. And for those viewing the archived webinar at a later date, contact Tensar at web@tensarcorp.com for the license agreement and software links. Thank you all for attending,